In this section, we are going to learn about some algorithm design strategy. So we are going to learn about the concept of recursion, divide and conquer, dynamic programming, greedy algorithms. So we just learned the basic strategy and we will look more details later. In this slide, we are going to learn about some algorithm design strategy, and we are focusing on the recursion. So what is recursion? What is linear recursion? And then the variant of recursion. Algorithm strategy. So what does it mean by algorithm strategy? In order to make an optimal solution, there are two fundamental components for finding the optimal solution for a computing problem. First, we need to formulate the problem clearly. And the other is we need to identify the appropriate algorithm design technique. So the appropriate algorithm design technique based on the structure of the problem for efficient solution. So every problem will have different way to solve it. So there are several algorithm paradigms. We can use recursion, or we can do with divide and conquer. We have dynamic programming. We can use greedy algorithm, and so on. So what I mentioned here are several algorithm paradigms that are popular. First is recursion. So we are going to learn more about the recursion, but let me just give you a basic understanding. It calls itself repeatedly in order to solve the problem until a certain condition is fulfilled. It has a base case and recursive calls. So later we will look more about the recursion, what is the base case and recursive calls. Just looking at this one, I have factorial 5. We want to call the factorial 5. So this is the function factorial n. So the function factorial contains of this condition. If n less than 1, then return 1. If no, return n multiply by factorial n minus 1. So the method factorial is called again. So we call this is recursion. So we will look more detail about this one. Divide and conquer. What does it mean by divide and conquer? We have one problem. We want to divide it into sub-problems. After we have sub-problems, we conquer. It means we solve the sub-problem until we get the solution of the sub-problem. We have the solution of the sub-problem, and then at the end we combine. It becomes one solution to the problem. So the divide and conquer paradigm divides a problem into smaller sub-problems. Then it solves this until you have the sub-problems, you solve it, and then you combine it. So the algorithms which use this kind of mechanism. We can see later the binary search, merge sort, quick sort, and algorithm for fast multiplication, Thracian matrix multiplication, and so on. In the dynamic programming, it explored the space of all possible solutions by decomposing the problem into a series of sub-problems. Okay, so the word sub-problem is similar with the divide and conquer. After we have the sub-problem, then combine the result to compute the correct solution for the large problem. So what is the difference then between the divide and conquer and dynamic programming? So the big difference is the divide and conquer algorithm. It combines the solution of the non-overlapping subproblems. Okay, so this is the keyword. Non-overlapping subproblem. In the dynamic programming, the subproblems are overlapping. So later, if you have a chance to learn the dynamic programming, so some of the subproblems here, they are overlapping. So we want to find the subproblem solution to get the solution for the last problem. There is another paradigm, we call it greedy algorithm. The greedy algorithm is to obtain the optimum solution from many possible solutions in each step. It tries to get the local optimum solution, which may eventually lead us to obtain the global optimum solution. Yeah. For example, if I want to find the maximum path for this node, so the greedy algorithm will try to find for every possibility. So 5 to 3 to 4 is on the arrow. And then it will check 5 to 3 to 17. It will check 5, 7 to 1. And then it will check 5, 7 to 2. And then, after we get all the values, we want to find the maximum value from the path. So the maximum value will be the addition. For example, 5 plus 3 plus 4. So what is the result? 5 plus 3 plus 17. What is the result? 5, 7, and 1. What is the result? And 5, 7 plus 2. What is the result? And then we check the maximum. So the greedy algorithm will check for every single step. Now let's just look on the recursion first. What does it mean by recursion? Recursion means when a method calls itself. So the classical example is the loop function. For example, like this one. The fn, I would like to get it from the fn minus 1. So in Python method, we can look at like this one. The countdown with parameter I. So let's say I want to print I, and then I want to go to I minus 1. It means if I define I equals to 3, then What does it mean? We have countdown three, and then we have print I. So we will print 3. We will print 3, and then countdown I minus 1. What is countdown I minus 1? We know I is 3. So we will call the countdown 2. Okay, so it decreases by 1. And then we will print I. So we will print 2. And then again countdown I minus 1. So I call again the same function. It will go down from 3 to 1, 0, minus 1, minus 2, and so on. So this will be infinite loop. Okay? I think you understand the infinite loop. Therefore, we need to have a Python method with base. Base, okay, we call it, this is the base, because when we have the base, we can stop the recursion. The previous example, we just print the value and then call the function again without any condition to stop. So we need to have a stopping criteria. Let's say if n is less than or equal to 1, return. So return means nothing, or this one means stop. Else we go to n minus 1. We can look at the formula like this one. Fn, if n less than 1, let's make it empty or nothing. If it is else, then call the function again and put the value n minus 1. We have the base case, or yeah, I put S this one because there might be several base cases. So let's just learn using one base case. Values of the input variable for which we perform no recursive calls are called base cases. There should be at least one base case. Every possible chain of recursive call must eventually reach a base case. It means if I have this countdown, let's say I put 3 when n equals to 3. So I need to know what is the base. Let's say I want to print only number higher than 1. Then the baseline is 1. If the number is less than 1, then stop. So that is the meaning by base. And the value, the possible chain of the recursive call must eventually reach a base case. So in this case, we are going to minus 1. Then if n equals to 3, if it is minus 1, it goes to 2. If n minus 1, then it goes to 1. So eventually it should reach 1. That's why we can put this one 1. The other things in the recursive, we need to have recursive calls. So we call to the current method. Its recursive call should be defined so that it makes progress towards a base case. So in the previous one, you can see there is a progress. The progress can be anything. For example, this one is n minus 1. Maybe you have n plus 1. That's also okay. Or you want to have n multiplied by 3. That's also okay. And so on. It depends on your problem. But the progress should at least reach the base case. Now, let's look at another example. This is a factorial function. You know factorial? If we have 3 factorial, means 3 multiplied by 2 multiplied by 1. So we can make this one similar to this countdown, but now we have a function to multiply. Okay. So the recursive definition is like this one. If n equals to 0, then it is 1. If it is not 0, then we have n multiplied by fn minus 1. So the base case here is 1. When n equals to 0, return 1. When n not 0, we do n multiplied by with factorial n minus 1. So we can look at this one. It is the recursion trace. A box, it means every recursive call. So the arrow from each color to the calling, and an arrow from each calling to color showing the return value. So for example, I have the recursive factorial 4. So I want to know what is the factorial of 4. Then after I call 4, it will check. Is n equals to 0? No. Because it is not 0, by the definition, this one. N equals to 0? No. Then it will run n multiplied by factorial n minus 1. It means 4 multiplied by factorial n minus 1. N minus 1 is 3. Again, in the 3, we will check, is it 0? No. Then it is 3 multiplied by factorial n minus 1, which is 2. So again, we check 2 multiplied by the factorial n minus 1, which is 1. So we call 1. N equals to 0? No. Then again, we have 1 multiplied factorial 0. n equals to 0, yeah, because it is already 0, so it return 1. The result of 1 will be here, because at the previous one we have 1 multiplied by factorial 0. So 1 multiplied by 1, it is 1. So the result of factorial 1 is 1. It will be here, because the previous one we call 2 multiplied factorial 1. 2 multiplied factorial 1 is 2. So this result will go here. In this case, we call the 3 multiplied by factorial 2. The result of factorial 2 is 2. So we multiply 3 and 2. It becomes 6. 6 is the result from the factorial 3. So we have 4 multiplied by 6 as the result of the factorial 3. And we got 24 as the final answer. Okay, so this is how the recursion works. How we can use this recursion? We have this simple search function. Now let's suppose I have a list. This is a list. And then we want to search a number 22. How can we search 22? This is index 0, index 1, index 2, and so on. So usually, we just say that, okay, let's try to find the index 22 from the index 0. If it is from index 0, if we start from index 0, we will check. Is it 22? No. We go to the next. Is it 22? No. We go to the next. Is it 22? No. We go to the next. Is it 22? No. And so on. Until, okay, this is 22. So it means we need 10 operations. Why 10 operations? Yeah, we do step by step. We go to index number 0, go to index number 1, index number 2, index number 3, and so on until index number 10. Yeah, we can make the function like find n comma data. So n is the number that we want to find. The data is the list. So if we have I in data, if n equals to n, then return I. Okay, we need 10 operations to do this one. Now, we have a recursive function with binary search. Before I explain the code, let me show you with the visualization. Okay, so this is, maybe I will show you the code first. We can do the binary search. We want to search an integer or the target in order list using this method, this function. The binary search, we have data, and then we can define the target. So for example, the target is 22, and we need to determine the low, and we need to determine the high. Here is the base case. If low is higher than high, then return false. If the condition is true, so if low is lower than high, then do this one. So in this case, we have the mid value. The mid is low plus high divided by 2. Do you know what is this one? Okay, this is to get the integer value. And if the target equals to the data in the mid, okay, this is true. If the target is less than the data mid, again check the binary value. Or if the target is higher than the data mid, again check the binary value. But the difference is now the low and high, the low and high, the low and high. Okay, so let's look at the visualization. So if the target equals to the data mid, it means if 22 is located in the data location in the mid, then we have found the target. But if it is not, then we recur on the first half of the sequence. If it is higher, then we recur on the second half of the sequence. Now let's look at the list that we have before. We have the list, and then we want to know what is the low, what is the mid value, and what is the high value. So how we can get the mid before? Mid equals to low plus high divided by 2. So this is the index, okay? 15 plus 0 divided by 2. So we know the mid is 7. And we will check. The target is 22. Is it equal to 14? Is it equal to this position? No. Okay. And then we will check. The target is less than the data mid. 22 is less than the data mid? No. The target is higher than the data mid? Yes. Then we will set up only the right side. So we don't need to consider this one because this number is low. Next, we need to determine what is the low, what is the high, and what is the new min. In this case, the mid is 25. We have the target is 22. 22 equals to 25? No. Then we need to check. 22 is less than data mid? Yeah. Because 22 is less than 25, we recur on the first half of the sequence. So we just consider this one. Now we have, this is the low, this is the new high, and this is the mid. Again, we will check. The target is 22. 22 equals to the data mid? No. And we will check. The target is lower than the data mid? No. 22 is higher than the data mid? Yes. So we recur on the second half of the sequence. So we will check this one. At this stage, this position low equals to mid equals to high. So using the binary search, we can find 22 with only 4 operations. Okay. So we do operation number 1, operation number 2, operation number 3, and operation number 4. It means with 16 data, I can do only 4 operations. We can make the approximation of the code is log base 2 of 15. Okay. Log base 2 n. So n is the number of data. In this case, our data is 16. So log base 2 16, then it equals approximately 4. Yeah, in this case, it is lucky we have 4 operations, but in some cases maybe it is 4. Some cases we can have 3. Okay. So usually we call this is approximation. It can be 3, it can be 5, or it can be 4. Okay. But yeah, the range will be in this value. In the binary search, it runs in log n. Because we already know, we try to reduce the searching time by looking the position of high and low. Every time we will check the high and low, and every comparison, okay, for every comparison, the mid and the low and the high will be updated. So for example, mid minus 1 minus low plus 1. Then after I know that it is in the left section, so I will update only the high. If I already know that it is higher than the mid, so I can update only the low. Thus, its recursive call divides the search region in half. So every time we cut 50%, 50%, 50%. There can be at most log n level. So we are not making n, but we can make log n for the binary search. What about the simple search? The simple search, it means you just go from the index 0, 1, 2, 3, 4, 5, and so on, and it will take n times. So if the data is 16, it means in the worst case, you will check all 16 data. So we call this is O(n) time. It goes to every element until n, and the process executes at least the worst case is n line. Then which one is better? Of course, we will look at the fastest algorithm. If you learn from the previous one, if you still remember, this one, constant is the best, and the second is log n, and the third is n. So whenever you develop an algorithm, if you can make very low, okay, it means this is the fastest one. If you can make a faster algorithm, then that will be the best one. Okay, for the linear recursion, it is just a linear, like what you already saw from the example. In the linear recursion, we have the base cases, and we have the recur, and the recur will be recur 1. So the definition is the same. For the base case, it begins by testing for a set of base case, and every possible chain for recursive call must eventually read a base case. And the handling of each base case should not use recursion. For the recur ones, it performs a single recursive call, and this step may have a test that decides which of the several possible recursive calls to make. But it should ultimately make just one of these. And it is to define each possible recursive call so that it makes progress toward a base case. When you make the recurrence, you need to go to the base case. Now we have a function linear sum. What is linear sum? We want to have like, if I have a number 1, 2, 3, 4, 5. So I want to sum all the numbers. 1 plus 2 plus 3 plus 4 plus 5. So what is the result? Okay. In order to do this one, we can make the algorithm. For example, this is the pseudocode. Okay, at the left panel, it is the pseudocode. We have linear sum a comma n. Let a is the integer array, and an integer n1 such that a has at least n elements. So we want the result will be the sum of the first n integers in a. Let's say I have 15 elements, but I want to sum only the n. Maybe if n equals to 5, then I just want to sum the first 5 elements. So if n equals to 1, then return a 0. If not, then let's do the linear sum. So we call again the linear sum by giving the data from a, and then we will do the n minus 1 plus a n minus 1. So you can follow this one, linear sum a comma 5. Then we will call again a comma 4, because this is going to n equals to 1. A comma 3, a comma 2, a comma 1. Then after that, we will return for every value in the a, so that we can do the summing. This is a simple of this is an example of the linear recursion. So what you already looked at the previous one, the factorial, this linear sum, and the previous one, the factorial, and then this counting, we call this is linear recursion. Okay, I will explain the other kind of examples on next week. Okay? And